There is a shape the ocean cannot stop making. Take a torpedo, pointed nose, thick middle, tapering tail, and you have just described a tuna, and a dolphin, and a shark, and a penguin underwater, and an extinct marine reptile called an ichthyosaur that died out 66 million years ago. 5 animals. A fish, a mammal, another fish, a bird, and a reptile. Separated by hundreds of millions of years of evolution, built from completely different ancestors, related to each other about as closely as you are related to a mushroom, and the ocean handed every single one of them the same body. This is not a coincidence, and it is not a one-off. The sea keeps doing this. It keeps taking wildly unrelated lineages and grinding them, independently, into the same handful of forms, the same torpedo, the same flattened bottom dweller, the same glowing lure, the same set of grasping claws. There is a running joke among biologists that evolution simply cannot stop turning things into crabs. It has happened at least 5 separate times. And the joke points at something genuinely unsettling underneath. Because if life keeps arriving at the same answers, over and over, from different starting points, then maybe those answers were waiting there all along. So why does the ocean keep building the same creatures? What forces are strong enough to override the accidents of ancestry? And how many of these shapes were, in some sense, inevitable? Tonight, we go looking for the ocean's favorite forms. To understand why the ocean repeats itself, we first have to understand the phenomenon behind it, and it has a name: convergent evolution. Most of the time, when 2 animals look alike, it is because they share a recent ancestor. This is called homology. Your arm, a bat's wing, a whale's flipper, and a horse's leg all contain the same bones, in the same arrangement, because you all inherited them from the same 4-limbed ancestor. That is the ordinary story of life, traits passed down, then modified. But convergence is the opposite, and it is far stranger. Convergence is when 2 lineages that did not inherit a trait from a common ancestor evolve it separately, because they faced the same problem and physics only allowed one good answer. The classic example is the eye. The camera-style eye of an octopus and the camera-style eye of a human are remarkably similar. A lens, an iris, a retina. But our common ancestor, some flat worm-like creature over 500 million years ago, had nothing of the kind. We did not inherit the eye from a shared source. We built it twice, independently. Because the physics of focusing light onto a surface has essentially one solution, and evolution found it more than once. And here is the key idea that makes the ocean so special. Convergence happens everywhere on Earth, but it happens most relentlessly in the sea. Because the ocean is a far harsher, far more uniform designer than the land. On land, an animal can hide behind a rock, climb a tree, dig a burrow, wait out the cold, exploit 1,000 little niches shaped by terrain and weather. Water does not allow that kind of improvisation. Water is 800 times denser than air. It resists everything that moves through it. It steals body heat 40 times faster than air. It filters out light within a few hundred meters, and it presses down harder the deeper you go, without mercy. These pressures are constant, planet-wide, and utterly indifferent to what your ancestors happen to be. Whether you descended from a fish, a reptile, a mammal, or a mollusk, the ocean confronts you with the exact same short list of engineering problems. And it turns out, there are only so many ways to solve them. This is why the deep and open ocean, more than almost anywhere else, behaves less like a canvas for infinite possibility and more like a set of locked doors, each one opening onto a solution that evolution is forced, again and again, to rediscover. So let us actually walk through the ocean's problems, one at a time, and watch the same monsters fall out of the physics. Problem 1. Moving through water fast. Water is dense and draggy, and if you want to chase prey or flee a predator, you have to cut through it with the least possible resistance. It turns out there is one optimal shape for this, and engineers have a name for it: the low-drag streamlined body, a form with a rounded leading edge and a tapering tail, sometimes measured by a value called the fineness ratio. The most efficient version sits at a ratio of around 4.5 to 1, length about 4.5 times the width. Now look at what evolution produced: the bluefin tuna, the mako shark, the bottlenose dolphin, the ichthyosaur. Measure their bodies and you find them clustering around that same ideal ratio, over and over, across fish and mammals and reptiles that never shared a swimming ancestor. The tuna and the dolphin even evolved the same crescent-shaped tail and the same technique of holding the body rigid while oscillating only the rear. One is a fish moving its tail side to side, the other is a mammal moving its tail up and down, and they arrived at nearly identical machines. This is convergence you can measure with a ruler, and speed is not the only movement problem the ocean solves the same way twice. Consider jet propulsion, escaping by firing a blast of water backward and rocketing forward. A squid does this by contracting its muscular mantle and shooting water through a siphon. But so does the humble scallop, snapping its shell. So, in a cruder way, do certain jellyfish, pulsing water to move. Completely unrelated animals, a mollusk, a bivalve, a jelly, all independently discovered that in a dense fluid, you can turn the water itself into a rocket. And then there is the apex predator problem. When an ocean needs a top hunter, something large, fast, and lethal enough to sit at the summit of the food chain, it keeps building the same creature. The megalodon, an enormous shark, held that throne for millions of years. Before it, giant marine reptiles like mosasaurs and plesiosaurs held it. Today, the orca and the great white hold it. These animals span reptiles and fish and mammals, separated by tens of millions of years, and yet the role sculpts them into the same thing: a large, streamlined, powerful body with a mouth full of blades, patrolling the open water. The ocean does not just repeat shapes, it repeats entire jobs, and it staffs them with whatever lineage happens to be available at the time. Problem 2. Living on the bottom. If your life happens flat against the seafloor, you face a different set of demands. Stay hidden, stay low, sweep the sediment for food. And the ocean's answer is to flatten you. But watch how differently it does it. A stingray is flattened top to bottom, its whole body spread into a disc, its ancestors having pancaked down from a shark-like form. A flounder is flattened side to side. It lies on one flank, and during its development, one eye actually migrates across its skull to join the other on the upward-facing side, one of the most bizarre transformations in all of biology. Two completely different routes. One destination, a flat fish on the bottom of the sea. Problem 3, the deep dark. Below a few hundred meters, sunlight is gone, and now the challenge is finding food and finding mates in permanent blackness. The ocean's answer, invented independently more times than we can easily count, is to make your own light. Bioluminescence, the chemical production of light using a molecule called luciferin, has evolved separately dozens of times across the tree of life. In fish, in squid, in jellyfish, in crustaceans, in bacteria. Some deep-sea fish even farm glowing bacteria in special organs, having struck the same bargain from opposite ends. And the specific trick of the anglerfish, dangling a glowing lure in front of a mouth full of teeth, has itself appeared in multiple unrelated lineages. Because in a world with almost no light and almost no food, a spot of glow that draws the curious closer is simply too good an idea for evolution to invent only once. This changes everything we thought we knew about how random evolution really is. Because these are not vague resemblances, they are the same specific engineering solutions, arrived at by animals with nothing in common but the water they were forced to survive in. That pattern goes deeper than shape. Take a fourth problem: sensing prey when you cannot see it. In murky or dark water, several groups of fish independently evolved the ability to generate and detect electric fields, reading the tiny signals every living body gives off. The electric fishes of Africa and the knife fishes of South America developed this power completely separately, on different continents, and even evolved similar brain structures to process it. And take a fifth: growing enormous on a diet of tiny things. The largest animals in the sea are not fierce hunters. They are gentle giants that filter clouds of plankton from the water. And this strategy too has been reinvented again and again. The blue whale, a mammal, filters krill through baleen. The whale shark and the basking shark, both fish, filter plankton through modified gills. The extinct fish Leadsichthys did the same over 150 million years ago, and the manta ray does it as well. Whenever the ocean fills with tiny drifting food, evolution builds a giant to strain it out, regardless of which animal it starts with. But there is one shape the ocean loves so much that it has become a scientific punchline: the crab. Somewhere in your mind, you have a picture of a crab, a flat, rounded, armored shell, a tail tucked underneath, walking sideways on jointed legs, waving a pair of claws. That body plan is so successful that evolution has produced it, from non-crab ancestors, at least 5 separate times. The process is called carcinization, and once you know about it, it is hard to unsee. True crabs are one group, but king crabs, the giant ones people eat, are not true crabs at all. They evolved from hermit crab ancestors, animals that once carried soft, curled abdomens tucked into borrowed snail shells, and they independently flattened and hardened into a crab-like form. Porcelain crabs did it separately again, from a completely different lineage. So did coconut crabs. So did hairy stone crabs. 5 lineages, 5 times, the same broad outcome: shrink the tail, widen the shell, armor the body, walk sideways. Biologists joke that everything is trying to become a crab, and there is a real principle underneath the joke. The crab body plan, compact, armored, low to the ground, with the vulnerable abdomen folded safely away and versatile claws out front, is an extraordinarily good design for scuttling across a seafloor full of things that want to eat you. It is defensible, it is maneuverable, it is efficient. So when different crustaceans face that same environment, natural selection keeps pushing them toward the same shape, like water finding the same low point in a landscape. But what is really surprising is what carcinization reveals about the limits of this whole idea. Because the convergence is never perfect. A king crab is not a true crab. Flip it over, and the differences are obvious. Its body segmentation, its legs, the number it walks on, the details of its anatomy all still carry the fingerprints of its hermit crab past. Evolution did not make an identical copy. It made a convincing costume over a completely different skeleton. And this is the crucial subtlety. Convergence is powerful, but it works on the outside, on the shape that meets the environment, while the deep architecture underneath, the inherited body plan, stubbornly persists. The tuna and the dolphin have the same silhouette, but the dolphin still breathes air, still nurses its young, still carries the bones of a land mammal's limb folded inside its flipper. The environment can sculpt the surface with astonishing precision. It cannot fully erase where you came from, which means every convergent creature in the ocean is really 2 things at once: a solution to a present problem, written on top of the frozen history of an ancient one. And here is what should genuinely unsettle you. If the ocean keeps forcing life toward the same shapes, It raises one of the deepest questions in all of biology. If you could rewind the tape of life and play it again, would you get the same result? The paleontologist Stephen Jay Gould famously argued no. He believed evolution was dominated by accident and contingency, that if you reran history, some tiny difference early on would cascade into a completely alien world, and nothing like us would ever appear. But the ocean's endless repetitions are the strongest evidence for the opposite view, championed by biologists like Simon Conway Morris. That convergence is so pervasive, so predictable, that the tape has, in effect, already been rerun, over and over, on different continents, and in different lineages, and at different times. And it keeps producing the same torpedoes, the same flatfish, the same lures, the same crabs. The eye alone has evolved independently dozens of times. If the same solutions keep emerging, no matter where you start, then the outcomes were never truly random. They were constrained, waiting, latent, in the physics of the planet itself. And the ocean has, in a way, been running this as a controlled trial without meaning to. It wiped the slate clean more than once. After the great mass extinctions, the one that ended the age of the marine reptiles, the one that nearly ended everything, the sea was left half empty, its top rolls vacant, its streamlined hunters gone. And each time, from whatever survivors remained, evolution refilled those same rolls with the same shapes. The ichthyosaurs died, and the dolphins rose to take their silhouette. The tape did not just get rerun in theory, it got rerun in the fossil record, and it kept giving the same answers. So step back and ask what this actually means, because it reaches far beyond crabs and tuna. The first thing it means is that life is not infinitely creative. We like to imagine that evolution can produce anything, that biology is a realm of boundless possibility. But convergence tells us the opposite. The set of workable solutions to any given problem is small, and often nearly unique. There is essentially one best shape for fast swimming, one basic logic for a focusing eye, a short list of ways to make light or to armor a body against predators. Evolution is not painting on an empty canvas. It is solving equations that have a limited number of answers, and the environment is the equation. The second thing it means is that we can, to a surprising degree, predict evolution. If you tell a biologist the conditions, dense fluid, fast predators, no light, a hard seafloor, they can tell you with real confidence what kinds of creatures should emerge, even without knowing which ancestors are available. That is a startling amount of predictive power for a process we usually describe as blind. The third implication reaches all the way off this planet. Because if the laws of physics are the same everywhere in the universe, and as far as we know they are, then the constraints that forge these shapes are not unique to Earth. Any world with a deep, dense ocean would present life with the same short list of problems: drag, darkness, pressure, cold, predation. And if convergence holds, then alien life in an alien ocean might not be unrecognizable at all. It might be swimming in a streamlined, torpedo-shaped body. It might have independently invented the eye. It might, somewhere out there in the dark water of another world, be waving a pair of claws. The ocean's favorite shapes may not be Earth shapes. They may simply be what water does to life, anywhere it happens. There is something almost humbling about all of this. We tend to think of every creature as a unique invention, a one-time miracle that could never happen again. But the ocean quietly disagrees. It has been running the same experiment for 500 million years, on fish and reptiles and mammals and mollusks and crustaceans. And it keeps arriving at the same answers: the torpedo, the flatfish, the lure, the crab. Because those answers were written into the physics of water long before any of them existed. These convergent creatures are not failures of imagination. They are something more profound. Proof that in a universe governed by physical law, life is not entirely free, and it is not entirely random. It is guided, shaped, and channeled toward a set of forms that were, in a sense, always going to be discovered. The monster was always down there. Evolution just keeps finding it. We are a young channel, still finding our footing in the deep. If anything tonight gave you that small, electric feeling of wonder, please consider subscribing. It takes about 2 seconds, it is completely free, and for a channel like ours, it is the single biggest thing you can do to help us keep making films like this. Thank you for descending with us. The ocean is still building its favorite shapes, right now, in the dark. We will see you on the next dive.